Today, we are going to delve into the world of decidable languages. These are special types of languages that have a very important property. They can be decided by Turing machines. So, what exactly does it mean for a language to be decidable? A language, let's call it L, is said to be decidable if there exists a Turing machine that possesses two crucial characteristics. First, it always halts, meaning it will never get stuck in an infinite loop. Second, it correctly determines whether any given string belongs to language L or not. In simpler terms, the Turing machine acts like a perfect judge, providing a definite yes or no answer for every possible input. Let's visualize how a Turing machine decides whether a string belongs to a language. Imagine feeding a string to the Turing machine. The machine processes the string and ultimately arrives at one of two states. If the string belongs to the language, the Turing machine will enter a special state called the accept state, signaling that the string is indeed a member of the language. On the other hand, if the string does not belong to the language, the Turing machine will transition to a reject state, indicating that the string is not a member of the language. Decidable languages have a couple of key properties that set them apart. First and foremost, the Turing machine that decides a decidable language always halts on every input. This means it will never get stuck in an infinite loop, regardless of the string we provide. Second, the machine will always enter either the accept state or the reject state. There's no other possibility. It will definitively tell us whether the string is in the language or not. Let's consider an example of a decidable language to solidify our understanding. Suppose we have a language L, defined as the set of all strings W, that contain an equal number of zeros and ones. This language is decidable because we can design a Turing machine that meticulously counts the number of zeros and ones in any given string. The Turing machine will then always be able to determine whether the string belongs to L or not. Here is a simple algorithm showing you how a Turing machine will check if there are equal number of zeros and ones. First, initialize two variables named count_0 and count_1 to 0. Then, iterate through each character in the input underscore string. If the character is 0, increment count_0 by 1. Otherwise, if the character is 1, increment count_1 by 1. Finally, return whether count_0 is equal to count_1. Now, let's compare decidable languages with another type of language called recognizable languages. Decidable languages always halt, meaning they provide a definite yes or no answer. Recognizable languages, on the other hand, may not halt in all cases. They might enter a loop for certain input strings. For decidable languages, the Turing machine will either accept or reject the input string. For recognizable languages, the Turing machine can either accept the string or enter a loop. Because of these properties, decidability is considered a stronger property than recognizability. All decidable languages are recognizable, but not all recognizable languages are decidable. Here's an important theorem that sheds light on the nature of decidable languages. A language is decidable if and only if both the language itself and its complement are recognizable. The complement of a language is simply the set of all strings that are not in the original language. This theorem provides a powerful characterization of decidable languages, linking them to the concept of recognizability and the relationship between a language and its complement. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.